Hey everyone, welcome back, and let's write some more Leetcode today. And you better not skip this video because we are finally going to be doing my favorite subject, some math. Let's get into it. Insert greatest common divisors into linked list. Very, very straightforward problem conceptually, but the math I'm going to show you probably isn't easy, but I think you'll understand it by the end of this video. And who knows, it might blow your mind. Take a look at this linked list. All we want to do is modify it. All we want to do is insert a node here, here, and here between two adjacent nodes. And we want to give it a particular value, which is the greatest common divisor. And we'll talk about that a bit more in depth, but just to kind of go over the basic part, imagine we have a pointer. We're maintaining a pointer. We're here. This is our current pointer. We're going to insert a node here only if there exists a next node, if the next node is non-null. Okay, then what do? Well, we take the next pointer here and set it to the new node that we're creating, and we set the next pointer of that new node to the next node of this node. So that's going to require a bit of pointer manipulation, but nothing crazy. The code will be pretty straightforward. And then when we update our current pointer, remember now that we have this node extra, we can't just shift by 1, we have to shift by 2 so that we get to this node, and then we can insert a new node in between there. And then after we do that, it's going to look something like this. The blue nodes are the new ones. The values matter though. The value has to be the greatest common divisor between these two. So a number that divides this and divides this without a remainder. That happens to be 6, because think about this for a second. The greatest common divisor between these two can't possibly be greater than the minimum of them, right? Like this could be the largest possible value that we have, okay? And then, a brute force would be just counting down from here. Try 6, try 5, try 4, try 3, etc., etc. That would be big O of n, where n is not the size of the list, but let's say n is the value of this. I guess I'll call that m. Obviously, in that case, the time complexity is going to be n times m, because we're going to insert roughly the same number of nodes that we have in terms of like the size of the list. And if each node takes this much to compute like the value of that node, that's going to be the time complexity. But there's a math algorithm called the greatest common divisor algorithm. It's Euclid's algorithm for doing that, a very famous mathematician. And that algorithm actually runs in log m time, where m is the minimum value between those two. That's actually a built-in function. If you just want to call the built-in function, that's perfectly fine. But I want to show you how to, implement this algorithm from scratch. It's not that long. It's like literally 3 or 4 lines of code. Most people can probably write it out. And if they can't, they can look it up and then memorize it or whatever. But I want to explain to you why it works. I want to clear every doubt in your mind. And don't you dare skip over this part. Suppose we have two numbers, 48 and 18. Their greatest common divisor, I'll just tell you, is 6. But how do you compute it? And how do you do it efficiently? Well, I'll call this A and I'll call this B. But this is the bigger number and this is the smaller number. But ultimately, this is what we're trying to do. The first thing that we could try is just check if this number divides that, then we're done, right? Because this is the largest possible factor we could have. So if this divides that, then we're good. Right now, it doesn't, right? If it doesn't do that, we care about what the remainder is. The remainder is the key. So I'm going to write out a formula. There is some value. It could be 1. The greatest common divisor between these two numbers could be 1. Like, for example, with 3 and 7, the greatest common divisor is 1. It could be 1 or it could be something else. But whatever it is, we call it G, the greatest common divisor. If B does not divide A, then we can't just write a very simple formula like A divided by B is equal to X, where B would be the greatest common divisor. We will have a remainder, and that remainder can be kind of summarized with this equation. Like in this concrete example, 48 divided by 18. Well, I think that's going to be 2 with a remainder of 12. The reason being 18 goes into 48 2 times and it becomes 36. But if we add another 18, then it's going to go over 48. So the difference, the remainder between these two is, of course, 12. That much makes sense. So if we take the bigger number and mod it by the smaller number, we will get the remainder, of course. In this case, that's going to be 12. Now, I'm going to tell you why the algorithm works, and then I'm going to prove it. We started with these two values. We're trying to find the GCD of these two. The next step is going to be for us to take these two values and find the GCD of them until we get to a point where we can do this operation and get 0. Because if the remainder is then 0, then we know that the smaller number divides both of them. And then that number will be the result. And you can kind of tell that this is going to be efficient. It can't possibly be more than log n because we're taking a number and dividing it. How many times can you take a number and divide it until it reaches 1 or 0? Well, that's like by definition of log n. And the base in this case actually is going to be bigger than 2 on average. But anyways, now let me prove to you why it'll work. I'll just kind of simulate the rest of it. So now we have 18 and 12. So now I'm going to take 18 and then mod it by 12. I get a remainder of 6. Okay, now I take these two numbers, do the same thing. I get 12, mod it by 6. Now I have 0. Okay, this is the magic number. We got 6. This is our result. But why does it work? Well, it kind of goes back to this formula and a couple key points. The first point is that any number that is a divisor of A and B is also going to be a divisor of B and R. Let's think about the extreme case where B is the divisor. B is the divisor of A. Well, in that case, R would be 0, and technically any number is a divisor of 0. And point 2 is kind of the opposite of this. Any number that's a divisor of BR, like a common divisor, is also going to be a divisor of AB. Now, if these two things are true, the reason this is important is because if these two things are true, then that means that the greatest common divisor of A and B is going to be the same as the greatest common divisor of B and R. So essentially, we're taking a big problem and turning it into a subproblem. And we're doing that repetitively until we get to a smaller problem that we can actually solve and understand. So now let me quickly demonstrate to you why these 2 points are true. Take a look at what we're doing over here. When we have 48 and we're modding it by 18, we're doing this. We're saying, okay, minus 18 once. Okay, it's 30. It's still greater than 18. Okay, minus 18 again. Okay, now it's 12. Okay, now it's not greater than 18, so now we're good. Isn't it true that if there's a value, I'll call it G or F, like a divisor or a factor, if it's a factor of 18, that just means that we can take that number, multiply it by something, and then get 18. In other words, like if we sum this up a few times, I don't know how many times, but then we can get to 18. For example, 6 is a factor of 18. You add 6 3 times and you'll get 18. And suppose that that factor is common to this one as well. So now I'm going to use the names for these. This is A, this is B. So basically some value G exists, which multiplied by, let's call it x1, will equal A. Like that's the definition of a factor. And let's say this is the greatest common factor, and it's also a factor of B. So B equal to G times, let's call it x2, some number is going to equal B. I'm starting to run out of space, so I'm just going to use this like white line as a boundary. So now I'm going to do A minus B, and that's going to be this minus this, but I'm going to factor out the G. I'm going to say G is this, x1 minus x2. So what this proves here is that any difference between two numbers, like A and B, if we take the difference between these, that difference is going to have G as a factor, right? And so when we are doing the mod operation down here, that's essentially what we're doing. We're taking the smaller number and subtracting it from the bigger one. So of course, we expect these to have the greatest common divisor. And then we do that operation multiple times. And of course, that should also have the greatest common divisor. So I just proved to you point 1. Anything that divides A and B is also going to divide B and R. I mean, the fact that it'll divide B is trivial, but I just proved to you that it's also going to divide the remainder. Now I'm going to prove to you the second point down here. And this I'll do quickly. Suppose there's a number that divides R, and I'll say R is equal to G times x1. Actually, I'm going to do x2 just because we know R is the smaller number in this case. And I'll do the same thing over here. B is equal to G times x1. Now, if you were to take these two formulas, substitute it in this, you'll get something like this. A is equal to this times Q. I'm going to factor out the G. I'm going to put G out there, and then on the inside, I'm going to have x1 times Q. And I'm going to put this, replace it with R, and I'm going to factor out the G's. So this is that. So G the greatest common factor of B and R is obviously a factor of A. I mean, this formula kind of proves it. You can divide both of these by G. This formula proves it. G times some number, this formula is going to be some number, is going to equal A. So I just proved both of these to you. I just proved to you that this algorithm works, and I'm going to code it up for you now, and you're going to realize how trivial it is. So let's code this up. First things first, let's just do the GCD part because that's going to be harder than the rest. So I'm going to start with that while it's still fresh in our mind. Okay, we have these two numbers. Let's assume that A is bigger than B, and I'm going to do this. While B is greater than 0, eventually it'll reach 0. We're going to do this. We're going to replace A with B. We're going to replace B with A modded by B. By doing it this way, we preserve the fact that this is always going to be greater than or equal to this one. And we're doing it iteratively because we don't want to do it recursively and lose memory, though it's possible to do this recursively. And that's literally it. So now you tell me, what's the return value going to be? Are we returning A or B? Well, B is eventually going to reach 0. When it does, A is going to be the greatest common divisor between them. And we know it's the greatest common divisor between them because of the subproblem. When we start with A and B and we replace them with B and the remainder, those two numbers are guaranteed to have the same common divisor. And so we keep doing this, we keep solving the subproblem until we reach the base case when one of them is 0, then the greatest common divisor between them is going to be the one that's non-zero. So that's why it works. And down here is going to be the easy part, the linked list part. So current is going to be at the beginning of the linked list, while current.next is non-null. The reason why we don't just do while cur is because we want to insert nodes between two nodes. So there must be a next node for us to insert the node into. So I'm just going to get the two values between the nodes, current and the current.next value. And then I'm going to create a list node. I'm going to give it a value of GCD of these two. So I'm going to copy that, do GCD of these two, and then I'm going to pass in for the next pointer of this new list node that we're creating. I'm going to pass in the current next node so that it can be connected with it. And then this, I'm actually going to assign to current dot next, and then after that's done, I'm going to shift current by 2. I'm going to set it to dot next, and at the end we want to return the head of the linked list. The head is not going to change because we're only inserting nodes between two adjacent nodes. We don't need a dummy node in this problem, just return the original head. Now, one question you might have if you're clever is, how do you know I put the max here and I put the min here? What if I put the smaller one? What if I put 18 for A and I put 48 for B? What's going to happen? Let's look at it. Well, A is going to be assigned to B. A is going to end up being 48, and B is going to be assigned to 18 modded by 48. Now, you tell me, what's the result of this mod? It's just going to be 18. If you take a smaller number and mod it by a bigger one, it's just going to be the smaller number. So the beautiful, the elegant thing about this algorithm is it'll actually fix itself. If you pass it in the wrong order, it'll still work. I mean, isn't that so beautiful? I would even say it's better than sex. Not that I would know, of course. Anyways, let's finally run this, and you can see it works, and I promise you it's pretty efficient. I think I probably had too much fun making this video. Anyways, have a good day. I'm gonna go back to working on my system design newsletter.